Good day, everybody. My name is Noah Lynch, and I have been assigned to present sections 11.1 through 11.2, Designs of Beams and Shafts. So in the previous sections of this course, they have all focused on analysis. Well, moving forward with these last few sections, they are going to focus on design. Shocker. So the main objective of these sections is to design members that can safely carry the expected loads while minimizing material and cost, which in the end is the goal of us as engineers for our employers. And so this is done by determining first the beam size, second the shaft diameter, and third the cross-sectional properties. Then on the right here, on the right, you can see an example of a beam under forces. So the first step on this fun journey is bending stress. So in the chapter, we are given that S equals I over C, and we can relate this to our stress equation, normal stress, and this gives us the flexure formula, which is S required equals N max over the allowable normal stress, where S is the section modulus, N max is the maximum bending moment, and sigma allow is the allowable bending stress. Then on the right, you can see an example of bending stress distribution through a beam. Next, we go to shear stress, which we are all very familiar with, which is shear stress allowable is greater or equal to Vmax times Q over IT with a rectangular cross-section, think like a hollow beam, is going to be shear stress allowable is greater or equal to 1.5 times Vmax over A. Then with a wide flange, which you can see an example of on the right, is going to be shear stress allow is greater than or equal to Vmax times the area of the web. So for the example, I chose an example from the book, example 11.1, which tasks us to find an appropriate beam shape that can carry the load of 40 kip, which is just to the left of the middle of this beam, and 20 kip, which is a force at the very right end of the beam. We are given the allowable normal stress, which is 24 ksi, and the allowable shear stress, which is 14.5 ksi. So using our shear and moment diagrams, which we derive from the given example in the book, we can determine that the Vmax is 30 kip. We determine that just by looking at the diagram and viewing that the lowest that it goes is negative 30. So that gives us our 30 kip. Then looking at the moment diagram, we can see that it goes down to negative 20, which gives us our 120 kip feet. So for bending stress, we can use our flexure formula, brand new and all shiny, which is the S required equals N max over normal allowable stress, which equals 120 kip feet times 12 inches over feet, all over 24 kip over inches squared, which gives us 60 inches cubed. So now looking at Appendix B from our textbook, we find the following beam to be adequate, the W18 times 40. We choose this specific beam because it has the least weight per foot out of the options available. So to determine the shear stress, which will allow us to determine if the beam is adequate, we use our stress equation for a wide flange, which is our shear stress average equals Vmax over the area, which is 30 kip all over 17.90 inches times 0.315 inches, which gives us 5.32 ksi, which is well below our maximum of 14.5 KSI. And so this confirms that we can use our selected beam, which was the W18 times 40. So the overall application of this concept is in this mechanics of materials class, we've been able to predict how the stresses would react in an existing structure. But with the new tools that we have been given, we can create safe, reliable, and efficient structural components, which is our entire task as engineers, which is to look at a structure, a future structure, I should say, and be able to tell our employers if it is adequate, and we'll be able to keep people safe and just be able to accomplish the goals that we have been given to do. So thank you very much for your time, and I hope that the future weeks and finals will go well for all of us. So make good choices, and may the Lord bless you.